I have the pleasure to be here with you online and talk about modular curves, isogeny estimates, and mathematics around these topics. So my talk will my course will be divided into two talks. And so I will give you the general plan for these for this activity, so for these two talks. So I'll start with a general introduction to explain what is the main question that I would like to understand with you. Then I'll make some, I'll remind you of some concepts, classical concepts, so elliptic curves, isogenies, and modular curves. Then I will do some height theory in various aspects. And then I will arrive to the main task that I would like to perform in these two sessions, which is computing the height of modular curves or discussing about the results we have on the heights of modular curves and modular polynomials. So the course has some intersection with other courses from the conference, which is of course a good thing because it enhances coherence for the audience. So you will see some concepts being revisited in Tilwin's lectures on elliptic curves, of course, and in Burgos-Gilles' lectures on heights in dynamical systems. So this is also a good sign. It shows that we have a lot of connections in this field of mathematics. So let me start now with the introduction. What is it that I would like to do? So in general, we are interested in understanding moduli spaces, classifying various objects, in particular classifying elliptic curves or abelian varieties. And often when you classify these elliptic curves or these abelian varieties, you add some special properties that you care about, maybe existence of torsion points, maybe existence of special maps, maybe existence of like a level structure, these kind of special properties that you care about and that help you understand the structure of the moduli space a little bit more. So we are interested in that. That's the prerequisite. We would like to understand more about some moduli spaces. Now, the main goal of these lectures will be to focus on certain aspects of a very classical moduli space, which is the modular curve x naught of n. So more specifically, I suggest the following question. Because these moduli spaces are so important, it is useful in some applications, but also just for the sake of knowing what's the size of this moduli space. If it is so useful, both in mathematics or in cryptography or in various aspects of mathematics, what's the size of it? How big is that? Is it difficult to find a model of it? Can you describe it, this x naught of n? And then if you can do that for any n, or for a family of n, of parameters n, how does it grow when this size, when the level n is varying? This is really the question I would like to understand. This has led to many things in mathematics, both in number theory, algebraic geometry, or even more analytic aspects of it. You will discover some of that. So I restrict my whole course on x naught of n. However, of course, this is a nice. It's also nice when you know how to deal with one moduli space, you can try to use some of the ideas to go beyond and attack some other moduli spaces. And there are works, in particular from some of the other participants in this conference and organizers that deal with other modular curves. So this is, this. I think there is work also to be continued there. So anyways, I'm going to focus on x naught of n. So x naught of n is actually an algebraic curve. So as an algebraic curve, there are very many ways to define its size. And so that will push us to define these ways, several of these ways, which will be an excuse to give you a little bit of height theory. So basically, we're interested in that specific moduli space. It is an algebraic curve. We can measure its size using various methods, various theories within height theory. And so it means that now if we have several methods to compute the size of this moduli space, it will be also necessary, or at least interesting, to have comparisons between these various measures. So from now on, I will follow the following program. I'm going to recall some properties, basic properties of elliptic curves and modular curves. And then in the second part, I'll define some height functions to measure the size of objects in algebraic and arithmetic geometry. And then I'll state and discuss the theorems which estimate the height of x naught of n using these various methods that we'll discover. So you will see part one is really classical. Part two is a bit of a festival of heights. So you're going to see a lot of different heights. And then part three will be really going deeper in the message that I want to convey. So what is the size of x naught of n? So I'm going to do that over the course of 2 hours, like this one and the one tomorrow. So don't fear if I'm not finishing all the slides. We have time tomorrow. Yeah. So all right. So what are we talking about? What are we classifying? I recall some facts about elliptic curves. Then I'll define modular polynomials. And then I'll do a little add-on, and I'll talk about an application of this in a discrete setting, because I think it might be interesting. So these isogeny graphs that you might have heard of. So okay, so let me pick a field. So we pick a field K. For the sake of this slide, we assume that characteristic is different from 2 and 3. And most likely, in what I'm going to say later, it's going to be Q or a number field, so characteristic 0. However, the theory, of course, exists in any characteristic, also in characteristic 2 and 3. It's just that the formulas are slightly longer. So my slide is small. I'm just going to do short formulas. So an elliptic curve over this field K is a smooth plane curve given by a short Weierstrass model. So this is a possible definition. Of course, there are other equivalent definitions. So what's the short model? A short Weierstrass model is this model, so this equation where A and B are fixed in K and X and Y are the variables in the plane. So this is an affine curve. Of course, an elliptic curve actually is a projective curve, so you can projectivize this. There is one extra point that you do not see on the affine coordinates, which is one point at infinity. So the curve itself, the completed curve, has one extra point. There is this condition. This condition ensures smoothness. This is the discriminant being non-zero. So the formula for the discriminant, of course, has a -16 in factor, but my characteristic is different from 2. So it doesn't, the vanishing is equivalent and non-vanishing is equivalent here. So, okay, elliptic curve just given by a short Weierstrass model. What do we do with these curves? Well, many things. They're very interesting from various aspects. And so in particular, they have morphisms, curve morphisms. And these morphisms help you change and compare how two models of this shape with eventually different A and B's can code for the same set of points over the algebraic closure. So you see, if you're given a curve like that, an equation like that, it might very well be possible that you find another equation like that of the same shape that codes for the same curve itself, for the same geometric object. So in that case, so this is classified. We know how to define these isomorphisms, and then if we have an isomorphism notion, then we immediately search for invariance. And there is indeed a very interesting invariant. It's called a J invariant, very classical object. Easy formula here because my characteristic is different from 2 and 3. So I have a very a very short definition for this J invariant. So 1728, and then you have 4a cubed. So this is one of the Eisenstein series. And then you divide by the discriminant. Discriminant is non-zero because you have a smooth curve, so this makes sense. And this element, if you start with A and B and K, is also an element of the field. It's this is the definition of the J invariant. The J invariant is called the J invariant because it stays constant in the isomorphism classes. So the isomorphisms, you can take them even over K bar. So this is a geometric setting. And it's a little bit more than that. This J invariant also satisfies the following moduli property. So if now I pick a number in K, there exists a curve E such that the J invariant of E is actually equal to the element I started with. You see, 4 is different from 3. Yeah, 3 says if I have two curves that are isomorphic, they share the same J invariant. 4 says if I take a number in my field, there exists a curve such that the J invariant is actually this number. So the first one is really the invariance of the existence of an invariant. The fourth one here is really existence of a moduli. So in a way, if you want, the moduli space of elliptic curves up to K-bar isomorphism is a line. The line given by all the elements in your field. Yeah? So for any element in your field, you can find a unique isomorphism class corresponding to it. So isomorphism up to K bar. So that's interesting to notice. I mean, it is invariant, but it's also a moduli. You can reconstruct your object using the element, which is one of the feature in the moduli space. Okay, so these are the basic objects in the construction of X naught of n. So these are elliptic curves. So now we have the curves. We need the maps. So let me now take n to be an integer, a natural integer, and let me consider algebraic maps between two such elliptic curves. So I'm going to ask that this map is called phi is surjective. So when we talk about surjective, it's over the algebraic closure, over the points, but over the points that are rational over K bar. Yeah. So I want a map that is surjective, preserving the group structure and of a degree n. So if you have all this, then you're an n isogeny. So as you can see, I'm now talking about the group structure. I did not redefine everything on the elliptic curves. So now one of the very important feature on these curves, these elliptic curves, is that they carry an algebraic group structure. So a group structure where it's a commutative group that has a very interesting structure, depending on the field where you look at. So phi being such a map is in particular a homomorphism of group. So it's both a morphism in the sense of variety, in the category of varieties, but also or schemes, in fact, but also on actually just groups. So this is a rich concept. You preserve a lot of things using these maps. So I mean, a priori, nothing tells you that such a map exists. If you take two elliptic curves, E1 and E2, they're not always isogynous. However, of course, if E1 is equal to E2, you do have examples. Well, I mean, non-trivial examples. So, of course, the identity is such a map, but you see, because you have a group structure that is commutative, you can just do the sum of points. So then so p plus p plus p n times will give you a map that we in general call the multiplication by n map. So the concept captures that as well. So you do have some homomorphism that are surjective over the algebraic closure. Okay, so then we have some maps now. And so if I give you two elliptic curves, the problem of finding whether or not these are isogynous, and then if they are isogynous, finding explicitly the isogenies, it actually is not easy. It's very useful in mathematics. We will see a little bit here with the modular curves, but it's also very useful in cryptography, since a good 20-25 years people have been using what is called isogeny graphs to encode messages. So in that case, your base field is a finite field, and then you try to understand path in some isogeny graphs of supersingular elliptic curves. So there are actually very interesting concepts also in slightly more applied fields that stem from this basic definition: elliptic curves and maps between them. Yeah. Okay, so we have some curves, we have some maps, and now we're going to use this. So the modular curve y not of n is an affine curve that parametrizes the following moduli problem, where you take the data E1, E2. So E1 and E2, they are two elliptic curves over the base field, and then phi being an isogeny in the sense that I described from E1 to E2. So now we are asking for phi to be an n isogeny, in the definition of point 1 here, but also cyclic. So what does it mean, cyclic? It's the kernel. So you know the kernel is finite because of the structure here, but the kernel being a subgroup in E1 has a structure of a finite group, and this kernel should be cyclic. So, I mean, you know the structure of n torsion on elliptic curves. At least it is some classical result. So, so over the complex numbers, it's something maybe easier to describe. If you use uniformization, you can see that it's really a z over nz cross z over nz. So a subgroup of n torsion is not always the subgroup of the n torsion is not always cyclic. So now, however, I mean, inside z over nz cross sz over nz, it's not too hard to count and to investigate which are the cyclic groups of order n. Yeah, so you're inside something of order n square that is a product of two copies of z over nz, and then you can choose a base. I mean, it's an easy exercise. So phi being a cyclic n isogeny is in 1-1 correspondence with the choice of such a subgroup. Yeah, it's good to know that, because sometimes you count these numbers, you count these possibilities for phi, and this is basically a count of subgroups. So it's good to have that in mind. So now what's the modular curve x naught of n? It's the associated projective curve. So you need to compactify this curve I mean, this curve a priori is not compact, and then you compactify it, and this is what we call x naught of n. So there are other definitions of these curves. In particular, if you start with the theory over the complex numbers, then you have the uniformization. You can see the action of congruence groups. You can really describe this data using actually J invariance and just a multiplication by n in one direction on the lattice. So there are ways to describe this very explicitly. You can find this in various classical sources. So you can really describe these curves explicitly over the complex numbers, for instance. Okay, so this modular curve, they are points. So a point on such a modular curve parametrizes, so corresponds to, up to isomorphisms, to a pair of elliptic curve together with a cyclic n isogeny. And so we are interested in this. We're interested in understanding when isogenies exist. We're interested in understanding how, I mean, is that frequent? Does that happen? Is that frequent? And if we can describe that very cleanly, how is it varying with n? This is basically what is triggering the research in that field. Okay, so I'm going to attack the theory from another angle and define what is called a modular polynomial. And you will see right away why this is relevant. So my goal here in point one is to define a polynomial in two variables. Okay, so I have a level. I'm going to take level n bigger or equal to 1. And I'm going to define a polynomial satisfying this property. Well, it's actually characterized by this property. So it's a polynomial with integer coefficients. And for any j, so I'm picking j an element of my base field. So it's a number. I specialize my first variable with j. And then I have a polynomial in one variable now, because I just specialize big X to be this number. And now I have a polynomial in one variable, and I want it to factor in this way. So now what am I doing here? I'm basically forcing what are the roots. Yeah, so I construct my polynomial like that in some ways. So phi n of j y, so j is fixed, is a product of linear factors y minus the j of e over c. So I need to explain a little bit the notation. So e is the elliptic curve I start with. And c here, I'm told c is varying among cyclic subgroups of order n, of e. Well, that's a very good start, because if you are interested in isogenies between E and another curve, an isogeny with a cyclic subgroup of order n, which will be a n isogeny in that case by the correspondence between degree and size of kernel, then I mean, this is precisely the subgroups you want to look at. Yeah. So now there is a concept of quotient of curves. So if you have a curve, you can take the quotient as a variety of the curve by this subgroup. And now this gives you something of dimension 1 that satisfies the exact same properties as E. It is also an elliptic curve. Actually, we do have even some formulas describing that elliptic curves depending on the formulas of the points in C, which are called value formulas. Anyways, this is a parenthesis. So this is an elliptic curve. This elliptic curve by construction will be n isogenous with a cyclic isogeny to E. So from E to E over C, you'll get the cyclic isogeny of degree n. So this is precisely what you care about. And you take the product over all the possible cyclic subgroups such that. So now you take this product, you kind of need to be a bit careful. It is a finite product. That's because you only have finitely many cyclic subgroups of order n in E. They are all subgroups of the n torsion, and the n torsion is finite. So this makes sense. And then, in fact, we can even compute them. We can compute this number. So psi of n, it's a number that will come back a bit later in the talk. It is I mean, it's n with a little product. So it's of the size, magnitude of psi of n is essentially n plus a little bit. Yeah. So for n is a prime, if n is L a prime, then this is L plus 1. This is just a choice of a base. That's rather easy to do. So we have psi of n cyclic subgroups, and then we construct this modular polynomial using this rule. So in fact, if you do so, you realize that the object you obtain is encoding precisely what you want. So it looks like we've solved our problem in a way. if such a polynomial exists, really, we have a plane model for the curve, for the modular curve. Why is that? Well, because now you can just let J vary over in your field, and it means that you're forming a curve such that each time you pick a point on that curve, they will be satisfying this rule that the couple on your curve will be actually be a zero of this, so they will encode for 2 J invariants of elliptic curves being n isogenous. And that's because any element of your field encodes for a curve. You remember from the beginning. So a J invariant, an element in the field can always be taken as the J invariant of a curve over your field. So that's a little bit what's behind. So, okay, we have a plane model. That's very useful. It seems that we can just do everything with this. However, there are problems, of course. Let me just mention 2 problems that pushed mathematicians to go beyond this to study the modular curve. The number 1 problem is if you have such a polynomial, the degree in x or the degree in y, you will see this polynomial is actually symmetric, is psi of n. This is the number of roots you have when you specialize. Yeah, so the degree in y is clearly this one, and in fact, because of symmetry, degree in x is also psi of n. And psi of n is rather big. I told you there's an exact formula for this, and it's bigger than n. So when n grows, psi of n is big. So the degree is big, and that has one consequence. This plane model will not be smooth. So this is one of the curse of plane models. If you have a plane model with very big degree, then you will eventually get singularities. And now, yeah, I mean, it's not forbidden to work with polynomials encoding for singular curves. Sometimes it's actually good. However, you have to be a bit careful. You cannot apply theorems on smooth curves if the curve is not given in the smooth model. So this is a little bit of a danger. So modular polynomials are very nice because they encode their model for your curve. However, they do have singularities. So fine, point taken. There's another problem, which is a bit of a different nature. The polynomial has a big degree, but it's known. So that's okay. I mean, we can deal with big degree. However, it also has coefficients that they are integers, so that is nice. However, these integers, they seem complicated. Not from my slide, of course, I didn't give you any coefficients here. But if you try to compute these polynomials explicitly, and maybe you're pushed by your colleagues in cryptography because they kind of need them for some work, then you quickly realize the coefficients are huge. They're very big, and that's something we need to understand. Yeah, what are the coefficients? How useful? So it seems very useful to have a polynomial describing what the moduli space is. However, how big is the polynomial? This is also a concern for us. We want to know that. Okay. I will give you an example of application, and that's isogeny graph. Let's imagine that I do have this plane model that I can compute this phi L. So L is a prime now. I decide for this slide to fix the level, so the degree of the isogenies in the game to be a prime number. So now I have phi L of xy. And then it's a rather useful polynomial if you have it, because it can help you describe what is called an isogeny graph. So what's an isogeny graph? Let me fix K is FQ. So in all that I'm saying, as soon as the characteristic is not 0, of course, it's co-prime with the degree of the isogeny. Also in what I said previously, you have to be a bit careful, of course, with that. So separability issues are important to keep track of. So here, if I pick K finite field, it has a characteristic, and this characteristic is different from L. Yeah. So let me pick a finite field, and I introduce an isogeny graph in the following way. So it's going to be a finite graph. I have some vertices, so I'm going to put a vertex in the plane, it corresponds abstractly to a J invariant. Yeah, it corresponds to an element of FQ. So I have Q of these points. I have Q of these dots. And then I'm going to draw an edge between two vertices, which corresponds to two J invariants, if and only if there exists an L isogeny between E1 and E2. So you pick 2 points. They correspond to elliptic curves. And if there's no isogeny of degree L, cyclic, of course, it's a prime, so it's going to be cyclic, then you don't draw anything. They're disconnected. But if there exists an isogeny, at least one, between E1 and E2, then you draw a line. That's the graph. Yeah? And nothing tells you that the graph will be connected. Maybe it's full of different connected components. Maybe it's a big connected component. That's the whole perk of this study, is try to understand maybe visually how often do we have L isogenies. So this graph is denoted GL of FQ. So L for the degree of the isogeny and FQ for the rationality of the J invariance. Okay, so take a second, maybe draw 2 points, call them J of E1, J of E2 on a piece of paper, and try to see if there is an L, abstractly, if there is an L isogeny between E1 and E2. If there is one, you place an edge, and if not, you don't. So what's so special about these graphs? These graphs are very useful for various reasons, but they're also rather fun. That's the reason why I added this slide. So these graphs, they look like volcanoes. So what do I mean by this? I mean, this is now it became the official name for their connected components. So in characteristic P, you have essentially 2 behaviors for elliptic curves. Most elliptic curves are ordinary. This is why we call them ordinary. They are just essentially 90% of the elliptic curves in characteristic P. They are ordinary, so their endomorphism structure is a CM structure. But you do have a few elliptic curves, so the remaining 10%, who are super singular, and their endomorphism structure is way richer. It's an order in a quaternion algebra. So you basically have two possibilities. Either the curves are ordinary with a little bit less endomorphisms, or super singular with many endomorphisms. The super singular ones, they live their own lives. So you will not see them in the next slide. The super singular connected component is actually the most used in crypto, but these are not volcanoes. You don't see the volcano structure on these ones. It's only for the ordinary one. Let me give you an example for these graphs when L is 3 and Q is 1009. So there it is. So I hope on the big screen you can see something. So what's happening on this slide? So you have a bunch of. So first of all, there's a lot of points. Yeah. So what are these points? Reminder: each point, like this point here, these are J invariants of elliptic curves over this field, F 1009. So basically, on this map, you have almost 900 points, something like that. I put aside the super singular ones. You don't see them here, but you have a lot of points. Yeah. And you see there are some edges, not a lot, but there are some edges. So for instance, here there is some fun structure where you see some kind of square, and then you see some little trees going down from the square, from the edges of the square. Yeah. So here, I'm pretty sure if you can see the points, pretty sure your eye went quickly to this one. It looks like there's a circle. So this circle is actually a 14 gon. So it's a regular polygon with 14 edges. And then also a little tree-like structure going down from each of them. And it's rather symmetric. Yeah. So you see, if you imagine that we are in a helicopter and this is some kind of volcano park, then you see this is the crater. And then the tree-like structures that go down, this is the lava flow. So we're seeing volcanoes from above in a way, yeah. And so, okay, the points are maybe a bit just a very small crater, maybe. But you see, this one is a crater with a pentagon, 5 gone here, and then going down with some lava flows, very symmetric structure, very beautiful. So a view from above of some volcanic structure. I mean, it's just a abstract way of describing what we have here. So what is it mathematically? This picture is a bunch of J invariants that are put in the plane, and each time you see 2 J invariants linked with an edge, it means there exists a 3 isogeny between the 2 curves over this finite field. So it means that in a way you're solving the moduli problem just by looking at it. So this means that you have all these points correspond to somehow points on the modular curve x naught of 3. X naught of 3 is here to detect, can I find a couple of elliptic curves with a 3 isogeny? And this data says yes. So the fact that you have these 2 red dots plus an edge means there is a point on, 1 point at least, on the modular curve x naught of 3. You see, because there exists this connected component. So I mean, this is I think it is very fun. I mean, if you like discrete structures, I would advise to go deeper over there. It's nice, and it's really connected with the arithmetic of the modular curve. So now the connection with the modular polynomial is the following. Modular polynomial is a way to detect easily, if you have the polynomial, if there exists an edge between these two dots. The 2 dots, they are explicit J invariants in F1009. You plug them in the formula for phi 3, if you have the formula for phi 3, and we have the formula for phi 3, so we can test. So we take phi 3 of the 2 numbers in F1009, and if you get a 0, if the polynomial has a 0 there, then it means there's an edge, and you draw your edge. So you see, and then you do that for all the combination of points, and this is how you reach this drawing. So anyway, so this is fun for the arithmetic of these modular curves over finite fields, but then also for some colleagues who are doing some crypto or more algorithmic questions. So that's we can interact there because we know things about the modular curve. Okay, but that was just a little bonus. So one of the applications of why we care about the modular curves. All right. So now I want to go back to my main line. My main line is I have this object x naught of n. It's an object that has been used in many places in arithmetic, and that is constantly used now, in particular in algorithmic or crypto. I have this object. I want to understand how big that object is. So to do that, I need what is called a height. So what's height theory good for? Well, it's mostly good for proving finiteness. So that's maybe the number one thing you have to keep in mind. The idea of a height function is you're interested in an object, or you're interested in a set. Let's imagine you have a set of things that you like. Then you have a function that tells you if this function is bounded, then you get finiteness. That's the perfect tool to prove finiteness. So the whole goal of height theory is to cook up functions that are clever and that reduce the problem of proving finiteness to a problem where you just prove the function is bounded. You see, there's a change because then you can do analysis, then you can use inequalities to prove that this specific function is bounded. So and the objects you look at, they might be way more abstract. So somehow it's a way to get an information by something classically perceived as weaker. It's easier to prove that something is bounded than to prove that a set of rational points on a genus 3 curve is finite. So this is the idea, trying to build up a tool to prove finiteness. So keep that in mind. Height theory, the main goal is that. However, there are other goals. So for instance, estimate sizes. It could be for algorithmic control if you are programming effectivity results for Diophantine equations, for instance. So effectivity results really proving that you have all the solutions for a system of equations. If you can bound the size of the potential solutions and sieve through that bound, then you really get an effectivity result. So I mean, having that kind of tool is of course very desirable. And then a bit more recently, there's what is called arithmetic statistics. So you see, each time you prove that the set is finite, you suddenly give work to many colleagues, maybe including yourself. Why am I saying this? Well, because if you say this set is finite, next question is automatically, okay, how big? How many points? What do you mean finite? Is it empty, or does there exist a point? Does there exist many points? Is it something growing with some parameters? Is it can we list them? You have a lot of things to do as soon as you know a certain set is finite. So arithmetic statistics, it's a little bit a way to formulate that you care about how the number varies, say in a family, or when a parameter is growing. You know, how many Galois extension of cyclic group of order 4 you have, or things like this, when the discriminant is bounded, and then you let the discriminant grow. These kind of questions, this is what height theory will, in the end, allow you to do if you can prove that you have these finiteness properties. Anyways, so height theory, this is good for this, proving finiteness, and then all the corollaries. So the theory is rather rich, but I selected some points that will help me convey the message on modular curves, and maybe also help you start with height theory if you have not seen that before, depending on your background. I'm aware you have different backgrounds. So the very beginning is the height of rational numbers. So maybe this is easy, of course, but it's nice to see it at least once, because it gives already the right idea of what you should look for if you want to define a height function in a more complicated setting. Then we move up to heights of algebraic numbers to do a bit more arithmetic. Then heights of projective points, because in the end we want to work with projective structures. So we start with points, and then we can do curves and varieties in the higher dimension. And then if you can do that, it would be really nice to be able to know how to compute the height of a moduli space, to measure how complicated the space is in some way. So now, as you've seen, some moduli spaces depend on parameters too, which means you can also let the moduli space vary. So why not taking a look at what's the variation of heights in a family of moduli spaces? So you see in these 6 points, you are you move up in abstraction in some way. So you start with the basic stuff, really quotient of 2 integers. Then you move up to algebraic numbers to do some algebraic number theory. Then you can do projective points on algebraic numbers. Then you can do curves and varieties. Then you can classify these objects. Then you can let the classifying space move as well. And you want to know how the height is varying in all these contexts. So that's what we're going to glance over. Keeping in mind what we have in the end, of course, we want some results on variation of height for x naught of n when n varies. So a little bit in the last level, if you want. Yeah. Okay, so let's start with the basic stuff. Maybe a bit easy, but still fun, I think. So take a rational number, take it non-zero just for because it's a bit easier. So define its height by the following. We take log max of p over q of p and q when the number we picked is taken as p over q. So r is just p over q. Well, p and q, they can be taken as integers, and you can even ask that the GCD is 1. And this is what you ask for when you compute the height. Yeah. Otherwise, if you just take log max of pq, well, it's not bounded. I mean, it's not well defined if you do not ask for some normalization. So you can also just fix h of 0 is 0. Yeah, so let me take a look at these examples. So minus 4 over 6, this is a rational number. It should have a height if my definition is well posed. So minus disappears because I take absolute value. The absolute value I take is just a regular one, max of x comma minus x. So just getting rid of the sign. So this is gone. And now 4 over 6, well, they are not co-prime. So first you need to get rid of the common denominator. And so in the end, you find 2 over 3. And the biggest of the two in absolute value is 3. So the height is log 3. Well, rather easy. So now I want to compare these two ones. Maybe we learned something out of that. So let me take 10,001 and 10,000 as two integers. I take the quotient. This is a rational number, and I want to compute its height. So now these two numbers, they are co-prime. They're just, you just take addition by 1. So they're co-prime. But so then you take the max of the two, but you just follow the definition. And then this is log of 10,001. Okay. So now if you type or 10,001 over, or you don't even need to type it, 10,001 divided by 10,000, that is very easy. It's 1 comma and then 0, 0, 0, 1. So most likely, depending on the context, of course, but if you ask anyone, maybe in the street, how close that is to 1, most people would say it is 1. I mean, 1 comma 0, 0, 0, 1. It's almost 1, really. Yeah, you're very, very close to 1. But what's the height of 1? Height of 1 is 0. Yeah, height of 1 is 0. So, I mean, it's just 1, 1. So log of 1 is 0. So height of 1 seems trivial. It seems that this function doesn't care about 1 at all. However, this function cares a lot about 10,001 over 10,000. Okay, so keep that in mind. So the problem here is not, so measuring the size is a little bit more than just taking the estimate with the Archimedean absolute value. Now, you see, the function knows a little bit more. In fact, you can be slightly more precise. You see, we say sometimes that heights measure complexity of objects. So the complexity of a rational number, it's not only its absolute value, its estimate as a number on the real line, if you want. It's a little bit more than this. You see, if you want to explain to say to a computer, what is this number precisely without any approximations, you kind of need a lot of digits. So that's the idea a little bit behind this this height. So it's very easy to describe 1, but it's a bit harder to describe this explicit number. You kind of need a lot of digits. So this guy is something like 4, maybe. And so the number of digits is something like maybe 5 for the numerator and for the denominator. So it's of this account. You see here the number of digits is 1, the height is 0. So maybe it's 1 plus the number of digits plus 1. No, height plus 1 is the number of digits, something like that. But anyway, so you see, you measure the complexity of a rational number a little bit better than just the absolute value. Basically, that's this slide. This is the basic height in the game. Okay, so let's move up in the theory. So now we have heights of algebraic numbers. So let me pick alpha, an algebraic number. Now we define its Weyl height by the following formula. So, okay, there's quite a lot of things. I don't know how much algebraic number theory you've done, but I'm going to describe quickly what is happening here. So this is just a normalization factor. Is you divide by the degree of what? The degree of a number field that contains alpha. So alpha is a number in Q bar, so it is algebraic. So there's a minimal polynomial for this number, which has a degree, and that gives you essentially a possible degree here. But any kind of bigger field that contains alpha is fine. However, the field needs to be a finite degree over Q. It needs to be a number field, so finite degree. So this is a finite number, yeah. And already you can tell that there will be a problem in the definition because I'm just I'm not specifying what the number is. So I kind of need to say something, right? A number field. So any number field containing alpha will give me a formula for the height. So all these number fields actually will give the exact same formula. And that's because of what is called the extension formula. So it's because of a link that exists between the absolute values of a field and its extensions. So it requires a little bit of study, but I claim that this actually does not depend on the field K. Yeah, this requires a lemma. This requires a little bit of work. Yeah, if you've never seen it before, then please keep that in mind. You can choose K the way you want as long as it contains alpha and it's a number field. But then you kind of need to prove that the formula makes sense. Yeah, it's still the same number that you get. And what kind of a number do you get? So there's a log max, a little bit like what happens over Q. Yeah, log max of the coordinates in a way of the coefficients. So we take 1 here, and here we take the absolute value, the v-adic absolute value of alpha. So now mk is the set of all the possible absolute values that we take up to equivalence. So we take only one representative for each equivalence place. And the choice that you make, you need to normalize your absolute value, is such that the product formula is valid. So the product of all the absolute values, the v-adic absolute values of alpha, if alpha is in K, the product over mk is 1, except if alpha is the 0 number. Yeah. So if alpha is 0, the height is 0. And then if alpha is non-zero, then you get the product formula. So extension formula for absolute values plus product formula for absolute values gives you a well-defined object or number here. Well, is it well-defined? I mean, we do sum over infinitely many absolute values, right? Because you have one for each p-adic place. So, and you have infinitely many primes. So a priori, this is a series. Of course, when alpha is a fixed number, this absolute value is non-trivial. So it's not 1, if and only if, it's not 1 only for finitely many places. Yeah, I mean, it's if and only if P divides alpha in some ways. Yeah, or maybe the numerator or denominator of alpha, if that makes sense. So this is a finite sum in the end, and it's well defined because of this extension formula and product formula for evaluations. And so we have now what is called the veil height of an algebraic number. So you see from the previous slide to this one, there's already quite a lot of mathematics, in fact, just to define this object. I mean, you kind of need to make sense of the whole valuation theory of Strovsky's theorems, normalizations of absolute values to make sure that you have both extension formula and product formula. I mean, there's quite a lot of things you need to know about algebraic numbers, yeah, to make sure that this works. And it's important to know that because this is actually the base of the definitions of more complicated heights later for projective curves or projective varieties. So it's good to see this example at least once. Okay, so now the second part of the slide is also interesting because it's a bit an account for why we define such an object. So this is a real number. The result of this is a positive or maybe non-negative number. It's a sum, finite sum of log max of 1 and something. So this is a sum of non-negative numbers, which leads to a non-negative number. So this is just a real number that is non-negative. And now this height, this function on Q bar satisfies what is called the Northcott property. So that's the dream we wanted to have for any height function. What is it saying? It's saying that the set of numbers such that the degree and the height are bounded above by fixed parameters, d and h, is actually a finite set. Yeah. So if you study algebraic numbers, if you want to prove you only have finitely many algebraic numbers satisfying something, one way, one strategy you can do is try to bound both degree and height. So the height satisfied this Northcott property. So finiteness gives you, boundedness gives you finiteness over a number field. Because over a number field, the degree is, of course, bounded by the degree of the field. And in that case, it's just boundedness of the height that gives finiteness of the set. So this is very, very nice, very important in Diophantine geometry. I do note that it's also fun to take a look at what's the smallest height possible. Now, smallest height possible is 0. And there are numbers of height 0. For instance, alpha is 0. It's an example. But there are others. So height of 1 is also 0. We've seen that before. But actually, any root of unity in Q bar is of height 0. This is actually if and only if. This is a theorem of Kronecker. So it's a fun exercise to do. And it also tells you something. You have infinitely many numbers of height 0 then, because you have infinitely many roots of unity. So where is the finiteness gone? Be careful. The degree also needs to be bounded. So the finiteness is really at the level of a number field, and inside a number field, you only have finitely many roots of unities. But over Q bar, you have infinitely many of them, and they all have height 0. Yeah. So this is important. Okay. So I've reached a point where I think my time is up for the first session. So I suggest that before moving up in abstraction and going to algebraic geometry with curves and varieties and their heights, we have the break now. I think it's tea break. And then we will see each other tomorrow for the sequel. Thank you.
Thank you, Professor Fabien. Maybe can you have a few questions if anyone has any?
Yes, of course.
Fabien, I have the following questions. So I think I never asked you this, but I mean, the genus of the modular curve x0L, L prime, is roughly L over 12, so linear in L. And if you look at your model and compute the genus from your model, I mean, the starting term will be the degree minus 1 times the degree minus 2 over 2, I think. So it's roughly quadratic in L, or even a little bit more. So can you say so you have to subtract quite substantially many singularities. Can you say something about the singularities of your plane model? In particular, multiplicities you have to attach to compute the genus in this way?
Hey, yes, so this is a very good question. I mean, so there is a formula for plane smooth curves for the genus, and then if you apply the formula for plane curves to compute the genus, if you apply the formula to the model we have given by the modular polynomials, indeed there is a very big cancellation. So I mean, one easy way to say is it's very singular. It's not like there's one little point. So there's very high multiplicities in the singularity. So I don't have it by heart, but they're enough to go from quadratic to linear. I mean, in the end, the genus will be psi of n over 12. I mean, 1 plus psi of n over 12, I mean, plus some smaller factors. And so yeah, absolutely. It's maybe when I said, oh, you know, the curve can be smooth, can be singular, it might be a problem. I was a little bit humble. I mean, the model is crazy. Don't use that model if you want to do algebraic geometry on the modular curves. Yeah, that's why people developed other approaches for. I mean, it's far from being a regular smooth minimal model. That's the opposite. Yeah.
Thank you.
Yeah, one more.
Sir, it's not clear to me that the modular polynomial should have integer coefficients, since the J invariants of like the numbers that the roots are in some arbitrary field, right? So there's some property that we probably need to get it into Z.
Yes, absolutely. So not only it's not obvious, but it's very important. So I mean, if you want the full proof, maybe you can go to this old book of Lang. But the fact that the coefficients are integral is very important for the following reason. It means you can use this description and use the modular curve to parameterize data for pairs of elliptic curves and isogenies between them over essentially any field. You see, the curve is not messing with you because it's the fact that you have integer coefficients tells you that in characteristic 0, of course, you contain Z, so no problem. You play with your field. And if you're in characteristic P, the first step will be to reduce mod P, but this you can do as long as you have some good reduction. And then you can actually still use the curve to get some information about what is happening mod P. So and then if it's over an extension of FP, you do you do your extension. This is not a problem because you have something that is defined over FP. So not only it is a very good question, not only it's not obvious, but also it is very useful. It's actually in the theory, it's important that if you have a moduli space and it's defined over Q, then it has a model over Z, and then you can use that in many situations, even if the fields are different. So that's good, yeah.
Any further questions? Not. Let's thank Professor Fabien Pazuki once again for this nice talk.